Hello everyone, this is Gayatri and today's video on Johnson-Cook parameter. How to find these parameter by using StressStrain Graph. In the previous video I have told you what exactly these parameter and why we are finding these parameters. And also I have told you if you are having the low strain rate or high strain rate, so which machines we are using to find the StressStrain graph. Now by these graphs, how can you find the Johnson-Cook parameters? That I will tell you through this video, and also I will show you through the Excel sheet, because then you can get exact feeling. If you are having the data like that, then how can you calculate these parameters? Okay, so let's start to learn how to find Johnson-Cook parameters through StressStrain graph. So the Johnson-Cook material model is what? Johnson-Cook material model when we are giving the coupled effect of strain. This is strain, okay, strain rate. This is strain rate effect, this bracket will give you, and this is temperature effect. So this coupled effect will give to the flow stress. Whatever effect will come through the strain rate and the temperature to the flow stress, that we will understand through the Johnson-Cook material model. So okay, we are having now the graph like this. This graph has just shown that this is true stress versus true strain graph at different strain rate, and this is quasi-static process and this is high strain rate processes, and we have found these graphs. Now by these graphs, how can we calculate these parameters? This is 1 parameter, 2 parameter, and this is 3, this is 4, and this is 5. So these all parameters, how can we find? Okay, if you want to see the detailing how these parameters will affect the stress strain graph and what is that and why this is required and all, so for that you can see my previous video, and I will give you the link in the description box. Okay, so one by one I will solve these things. So first, if you have to find these 3 parameters A, B and N. So how can you find these parameters? So first, for that I will take only first bracket. A first bracket is like this: sigma equals to A plus B epsilon power of N, and this is strain, this is true strain, okay, true strain, and this is true stress. Okay, so this graph I will find through the quasi-static process at very low strain. So at low strain, whatever graph you will find, suppose you are using the UTM machine and you have find this type of the graph at low strain, like that it will keep on increasing, and this is true stress. Your y-axis is true stress and your x-axis is true strain. Okay, so how could you find these parameter? By using this graph, this type of the graph. Some data points are there like this, like this, like this, and you are finding this type of the graph by using UTM machine. So okay, so now you can do sigma minus A. We can transfer this A here, equals to B times epsilon N. So now we take ln in the both the side. So ln is log of base E. So ln of sigma minus A equals to ln of, this will be equals to, because it is in multiplication, it will go in an addition when you are using ln. Okay, so it will be N times ln of epsilon. So this true stress and true strain which we are finding through the quasi-static process by using UTM machine. Suppose your strain rate is this time, because this time strain rate is very low. So suppose your strain rate at this time is equals to 1 per second. Okay, like that we are taking. Now for that, what you have to do, this versus this, if I can make the graph, because we are having the data of ln of sigma, or A is what? A is equals to the yield stress of the material at reference condition. So reference condition, whatever strain rate is you are taking. So this time in a quasi-static process, here somewhere you are getting the yield stress. So that you have to put, that you can find through the stress strain graph. So like that you can make the graph between ln of sigma minus A versus ln of epsilon. This is true strain, this is true stress, this is yield stress of material at reference condition. So okay, like that, suppose you are finding this type of some data, okay, data points, and if you are making the trend line on this data line, and you are getting this type of the line. So what is the slope? So slope will is nothing but n value give you. And what is the intercepts? So intercepts will give you the ln b value. Okay, so we can find through that. So suppose ln b equals to x, some value you found, and so b will equals to e to the power of x, and n is exactly whatever slope you are getting. So you can find through this. Now this same thing I will show you through the Excel sheet if you are having some data points. This is not whatever data points I will show you, that is not related to exactly any material, but just getting the feeling. If you are having this type of the data points, then how can you find this type of the parameters? So this is your quasi-static data. So you have find at a tensile test, if you are having the strain rate suppose 1 per second, at that time you have find this type of the data. This particular strain you have find this particular stress. So this is true strain versus true stress data you have find. So this is your x-axis, this is your y-axis. So this type of the graph you will find. Okay, I will show you how you can make this type of the graph. Okay, just you have to select these data points and insert, and you can go for the chart and whatever you like. So accordingly you can make the chart like this. So the same type of the chart you are finding here. So now you can put x-axis, y-axis and all that detailing I'm not going, just you are finding this type of the graph, true stress versus true strain graph, and this is your yield stress point at the reference stress. Why I am calling this reference strain rate? Because this strain rate you will follow as a reference for finding some other parameters like C. So this point you can directly find. So here we can see it's approximate 300. So A we can take is a 300. This is yield stress. Other points you have to find. You have to find B and N also. So okay, for that what you can do? Okay, first you can delete this because already I have made this graph. This is graph and I have mentioned this y-axis and x-axis is what is not complete for the report point of view, but okay, just for showing you how it will looks. Now as I have shown you the sigma minus A versus of ln of E. So ln of sigma minus A versus of ln E, that type of the graph you have to find. So sigma minus A you have done. So this is stress and we know the 300 value is there. So this is how much? This is B3, whatever stress value minus of 300. B3 minus 300. Similarly for B4 minus 300. So this sigma minus A I have done through the stress line. These are two lines, these two columns you have find through the UTM machine, and accordingly I can solve these type of the values. So sigma minus A you can use by this B column you can find. Now the D, this is your E. E column is what? E column is whatever E value you have find, that is ln of this. So ln of this value, ln of A3. Here the formula is showing. Okay. So ln of A3. So you can find this and you can drag it and simply you can find this value like that. You can drag it if suppose nothing is below. So for first line you can point out this formula. So whatever formula is there you can put it here, the formula, and then simply drag it and you can find the value of ln E. Now ln of sigma minus A, because we have to find the graph in between of ln of sigma A minus A versus ln of E. This will be in your y-axis and this will be in your x-axis. So some value are this type of minus 300, that the ln value will not solve. So whatever value is not solving is okay, and other in between some values we can find. So here just I have shown some points, only 79 data points, but it is not show. Actually it is 10,000 data points you will get. So for the showing purpose, just points I have taken, and it's not related to actual any material. So okay, now we will make the graph of ln E versus of ln of sigma minus A like that. So insert, simply chart and make the graph exascalated. If you are using this type of the type, there's a line only, so it will show like this. Okay, so this is similar I make here. proper graph. Proper, I have kept the value what is in ln in a y-axis, what will be in a x-axis, like that. So I will explain in this graph. So it is like that, simply you have to find. Okay, so now if I will delete it and I can use this graph. Now you can put the trend line on that graph. So this is the trend line. Okay, so how can you find this trend line? If you are just deleting this trend line, whatever trend line initially was there, if you are deleting and again you are putting one trend line, so it will be linear and also show the equation. You are showing the equation because linear, because it's a ln of sigma minus a versus ln of epsilon. So it will be looks like this. So you can set this value also. So formulate the tail line equation. Now it will be looks like that. So you can choose the number up to 2 decimal only. Okay, so you can choose and it will looks like that. So whatever in x is ln of strain and fx is ln of sigma minus a. So it was ln n times of ln of strain. So n value, what is n, is 0.8 and this is ln b. So this is equals to, if your ln b equals to 7.1, so b equals to e to power of 7.1. so exponential you can take, so it will be 1 to 1 1. So we can say 1 to 1 2. That much MPa is your b value. What is n? What is b? B is strain hardening constant and n is strain hardening coefficient. So you can find through this graph. So okay, I can repeat once again. You have find this type of the data points from by using UTM machine, and then you made the graph like this. From that you can find the A point, which is the yield stress, and then you have to find the B point. So for that you have taken the ln both the sides. So ln of strain and ln of stress minus of A. So that you made the graph like that and you set the trend line, and this is equals to n times of ln of strain. So this value is gives ln, and n is what? N is strain hardening coefficient, and this is your ln b value, and from the ln b you can find the b value. This is strain hardening constant. Okay, now we will go for the second bracket. Okay, now we have to find the third parameter c. Okay, for that what we will do, take both the brackets, because this is our reference strain rate bracket. So for that we can find the what is the effect will come at different strain rates. So for that we have to require this first bracket also. So for finding the c parameter we will use both the brackets. Plus b epsilon power of n, this is first bracket, and 1 plus c times ln of strain rate star. Okay, so this is the ratio of, this is actually the ratio of strain rate at which strain rate, high strain rate you are finding, and the reference strain rate. Reference strain rate in which your quasi-static process you have used this bracket as found by using the reference strain rate. So okay, for that what you will do, now you know the value of a, b and n, these three parameters now you are knowing. So okay, you can put sigma upon a plus b epsilon n power, these things you can put it here, and this is equals to 1 plus c times ln of epsilon star. Okay, like that. So you can find it. Now this is stress versus strain graph. This is strain, this is true stress, and this is true strain. Okay, true strain. So this value we will find for different strain rate. Whatever strain rate, suppose we are taking 1000 strain rate, 1, 2, 0, 0, 1200 strain rate, suppose 2000 strain rate. So like that, if different strain rates are there, at that time whatever true stress versus true strain value is there, we will find the graph between this is in y-axis and this value in x-axis. So whatever slope will get, that will be your c parameters. So okay, now intercept is also given. This is one intercept. So suppose this type of, you are finding the data points and you are finding this type of the graph, and this is suppose one value. So whatever slope is there, that slopes will show you c, strengthening coefficient of strain rate. So okay, now we will see these things through the actual graph. Okay, so this is the data we have found, true strain versus true stress data at 1000 strain rate, and this is the data at 2200 strain rate, and this is the data at 3000 strain rate. So like that we are finding the data to strain versus to stress graph. So now we have to find the C parameter. So how could you find the C parameter? For that, what you have to do, you are having the true stress versus true strain graph at different strain rates. So first strain rate was your 1000. So this is same value, 1000 strain rate was there. For that we have found the true strain versus true stress values by using some impact machine or some machine. From any machine we are using some impact in which we can find the graph of high strain rate graph. So we can use split Hopkinson bar also you can use. From that you can find this true strain versus true stress graph at the strain rate of 1000. So like that you have find. Now you have to find this sigma upon a plus b epsilon power of n, this value. So for that simply what you did, this value, all the value you are having, because we are having a value, b value, n value, and what is this epsilon? This is this A2 strain rate and this is stress value. Okay, so simply you can find sigma or epsilon you can put for this particular strain rate. Okay, for that you are using stress and strain for quasi-static process. For that strain rate is 1 per second. Now strain rate is 1000 per second. So for that you have find this true strain versus stress graph, and that stress and strain value you will put here. Okay, not this, that is different and here is different for different strain rate. Okay, and similarly you have find this graph for 2200 strain rate. Okay, for that this is the strain value, this is the stress value, and again you have find this value and this so this value. So okay, so this will be x-axis, this will be y-axis. Now for the strain rate at 3000, for that also you have found this true strain data to stress data by using some machine, and then you can calculate this ln of this value and this value. Okay, so okay, this was I have taken ln of 1000 only divided by reference strain rate we should do, but we know reference strain rate is 1 only, so whatever you will divide the same value you will get. So okay, for that I have not divided. If you are having the strain rate, what reference strain rate 0.01, so for that you have to divide with 0.01, then this will be ln of 2 more 0 will be there, 1 after 50 will be there. Okay, so here our what we have taken as a reference strain rate, that is 1 only. So for that 1000 divided by 1, which is equals to 1000 only. So similarly we have done. So okay, now we have to make the graph. So okay, this is the different strain rate. I have made the graph true stress versus true strain graph. Now we can use this step of the graph, that is true stress divided by sigma. This is sigma value, sigma divided by a plus b epsilon power of n. Actually I have not shown properly because our main focus how to make the graph. Now how it will show to the report. So this is not like this we cannot write for if we are presenting in the report. So okay, so this is ln of strain rate. So we are having 3 strain rate, 1000, 2200 and 3000. So this is for 1000, this is for 2200, this is for 3000. Like that we are finding the data, and we can make the trend line of this data. Likewise I have shown you for the quasi-static process how to make the trend line, and there are after the point decimal point there are so many numbers are given. So how can you format that things also, that trend line? So that also I have shown you. So this step of the value you are finding. So what is this? Fx is this value and this is ln of strain rate. So this is what? This is your C value, and here I have forcefully given the intercept is 1 because in that equation the intercept was 1. Okay, here I have not using any particular regression method or any optimization. I am not using any spatial algorithm for using the proper optimization of this data. So that is separate thing you can find by using this step of the regression analysis and optimization and all. You can use some particular algorithm for finding the exact what line will be there. Here just I have shown if you are finding the data. So likewise you can, this is the raw figures. So how can you find this type of the value. So this is 0.02 is your C value. Okay, here from the different strain rate you have found this C value. So C value is what? C value is 0.02. Now the last parameter is M. This is fifth parameter. So now we have to find this parameter which is depends on the temperature effect. So whatever the temperature effect is going on the flow stress, that we will see, and according to that we can find the flow stress versus strain graph, true stress versus strain graph, and then we can find this M parameter. So for that also we have to take first bracket and this last bracket. Actually this first bracket is always we are taking if we are finding the C parameter or M parameter, because this is our reference bracket. So whatever we are taking, this is our reference stress. So reference things we always have to take. So accordingly for finding this M parameter we will take first bracket and this third bracket. Okay, if I am taking first bracket, that is A plus P epsilon power of n, this is epsilon power of n, and last bracket, that is 1 minus T to the power of m. Okay, so if I am taking these two bracket for finding these M parameters, so for that what we will do, first I will transfer this first bracket here left hand side. So this will be sigma upon A plus B epsilon power of n equals to 1 minus T to the power of m. So here m is in power, so I have to transfer this 1 also. So this will be equals to 1 minus sigma upon A plus B epsilon the power of n. So this will be one bracket, okay, like this, and here it will be T to the power of m. Now we will take the log with the both the sides. So ln of 1 minus sigma upon A plus B epsilon power of n, okay, and this is equals to m times ln of T. So for different temperature, for particular temperature like you have taken 273 Kelvin, 400 and 400 Kelvin, so like that for different temperature you have find the stress versus strain graph. So for stress you can put here, strain you can put here, and A, B, N already we are knowing. So if you are making the graph, so this will be your y-axis. Suppose this value is your y value, so this is y value and this ln t. So here is x-axis in ln t, and suppose you are finding some data points like this and you are fitting the trend line, so it will be like this. So whatever the slope will be there, so that will show you M parameter. Now I will show you through the Excel graph. Like that you have find the strain versus stress graph for different temperature. So here I have taken only two temperature, 923 Kelvin. So this is for 923 Kelvin, and one more graph. This is true strain versus true stress graph. This is one graph, true stress versus true strain graph for the temperature at 923, and this is one more graph, true stress versus true strain graph for temperature at 473. Okay, so here what I have done, so this will be ln of temperature. So whatever temperature is this, ln of that temperature. So this is same value all around, and here in y-axis. So y-axis, how can you calculate that formula I have explained to you. So accordingly you can put ln of 1 minus of B2. B2 is nothing but your stress value divided by A plus B into epsilon. Epsilon is your this true strain value at that temperature, okay, and the power of n. So this A, B, n value we know, and this stress and strain value we have taken from here. Okay, so accordingly we have find the x-axis and y-axis, and this is similarly for the temperature 473. I have found x-axis for ln of 473 and y-axis the same formula I am using. Okay, so like that there are two values, there are two temperature, that is 923 and 473. For that we made the graph like this. So because this value only, this y-axis value only will increase, because in x-axis the value is same. So for that particular temperature, so here like that two temperatures are there, and if I am fitting the trend line here like this, this is our trend line and is showing the slope. So this is showing minus of 0.64 and plus of 2.74. So this M value, this is showing your M value. So M equals to coming minus of 0.64. Okay, now this is our final. So we have found these parameters, this Johnson's Cook parameter, by using the stress strain graph which we found through the UTM machine or any tensile machine. Okay, so this is our first bracket. So this is our first bracket. This is A, B and N. A plus B epsilon, it means to strain power of n. So we can find through this graph, just as I have shown in you in Excel sheet, and this C value 0.02 that I have found through the stress strain graph for 3 different strain rate, and this is the M value which is depends on the temperature, and for 2 particular temperature I have found this M value. Okay, so if you are having more strain rate or more temperature, you can find that. So this value is not actual related to any particular material or particular strain rate or particular temperature. This is just like that I have given you for showing how to calculate if you are having the data of like this is to stress versus to strain data. If you are having, then how can you find these parameters? So okay, so in this video I have explained you if you are having this type of stress versus strain graphs, so how can you find these parameters. If this video is helpful for you, so please like and subscribe, and thank you very much.